Thank you so much for the nice introduction to Dr. Nageswara sir. Uh, Yeah, just now first time interacted with him, and I just am very much impressed with his great profile, and he's doing well. And I would like to appreciate the Optical Sensor Council to just make this optical sensor cluster and to start this monthly webinar series. And I'm glad to be a part of this webinar 5. And I personally know I worked for around 4 years with Professor Carlos Rios, and he is a very great leader and great motivator and mentor. So I have also gone through the several talk and plan with the of the this webinar. So this is really is a great initiative. So that will be very helpful for the people who are working in the sensors. So in line with this, thanks for the invitation to me, and thanks to Professor Carlos Rios, and Dr. Nageswara sir to invite me for this talk. So uh, I think this is for 1 hour. I want to confirm. It's 1 hour, right, sir? Talk.
Yes, 1 hour. You can leave Q&A about
Yes.
10
So I will
minutes.
complete in 45 or 50 minutes. Yeah.
Okay. Thank you. Yeah.
So yeah, so today in light with the sensor, I would like to give a talk on the some healthcare application, and our team has last 6 year around. I work in the China, and still my one of my team member is working in Laucheng University. Just recently last month I was in Laucheng University. So we have developed one new kind of the sensor, that is the Waveflex biosensor. So this is kind of the made with the optical fiber, and but this is the flexible in nature, and as well as this kind of the sensor is based on the plasmon wave. So we have given this newer terminology, that is the Waveflex biosensor. And also the sensor structure is quite new and different than the conventional sensor or conventional tapered sensor. So I'll discuss everything in the detail in this next 1 hour session. So here, first of all, I would like to discuss about that why this kind of the sensor is important, or why healthcare is important. So we have recently passed with the just very what scenario in the last few years. So these are the few data of the World Health Organization, and that we can see due to the cholesterol around 2.6 million death occur each year, and due to the liver around 2 million death occur each year, and due to the cancer around 10 million death occur in 2020, and this yearly it is increasing. And due to the diarrhea, especially in the villages, and small for the small in the small children, around 0.6 million deaths occur each year if we will not cure on the time. So question is that how we can reduce this number. So for that, the only one effort we can do, that we can develop the portable, scalable, and affordable early diagnosis technique. Through that we can diagnose these things in the early stage, and then we can go for the treatment, and then we can cure these things and quickly. So in line with this, we have done one effort to develop this new kind of the sensor. So I will discuss about this. What are the advantages in our sensor? So first of all, I want to discuss that what are the healthcare optical biosensor. So in healthcare optical biosensor, we can see there are three things are very important: the sample, biorecognition element, and optical transducer. Sample may be the like any kind of the biomolecules like glucose, cholesterol, urea, uric acid, any kind of the things, or some cancer cell, bacteria, anything. So for particular detection of these kind of the analytes, we need the some particular biorecognition element, that is very essential for the biosensor. Okay, so as a biorecognition element like enzyme, antibody, protein, nucleic acid receptor, these are the essential, and that is very specific for the biomolecule. Like if you want to develop the glucose sensor, then we need to use the glucose oxidase enzyme, and that will only react with this glucose, and then we can that can produce the gluconic acid and hydrogen peroxide. And so the hydrogen peroxide amount will depend on the concentration of the glucose. So this hydrogen peroxide will change the refractive index value surrounding the sensor part. So that can be sensed through the several transducers. So many transducers like SPR, LSPR, interferometer, resonator, gratings, refractometers. So these can sense the changes, and we can that give in the form of the signal. So we can see that if there will be any variation in the signal, and then we can able to identify the concentration, and as well as we can also able to identify or segregate the type of the molecules, biomolecules. Okay, so I will discuss how these sensors work in detail. So question is that why optical fiber, and what are the advantages of optical fiber sensor? So first of all, see that what are the application of the optical fiber. So nowadays there are wide application of the optical fiber sensor. So many kind of the optical fiber like single mode fiber, multi-mode fiber, hollow core fiber, plastic optical fiber, multi-core fiber, photonic crystal fiber are widely used to develop the different kind of the sensor. So that sensor we can divide into three parts like chemical quantity detection, physical quantity detection, and biomolecular detection. Okay. So in physical quantity detection like vector magnetic field, temperature, humidity, curvature, we can develop. Similarly, in chemical quantity like pH detection, chemical reagent, gas concentration, heavy metal ions can develop. Okay. So similarly, our focus is on the biomolecular detection, that is the amino acid detection, bacteria detection, or protein molecules or cancer cell detection can mm, developed with the help of the optical fiber sensor. So overall, we can see like uh, even for the daily use applications like um, to detect the gas concentration at home, or heavy metal ions in the water molecules or drinking water, or some pH detection of some of the things, humidity, temperature, and as well as some of the place bacteria grow. So these things are common in our home. To detect these things, we can develop the sensor, and that can be used in the hometown, and uh, so that our family will be happy. Okay, so this kind of sensor can be useful for the daily day-to-day applications. So question is that what are the limitation of the conventional sensor, and what are the advantages of our sensor? So there are wide so many advantages. I will not discuss in detail, so that because everyone is aware about these things. So like first one is the biocompatible, and we can use in any kind of the biofluid, or even in saliva or serum, and because the optical fiber is made of the silica, so that will not react. The second one is the reduced size, flexibility, and low weight. So due to the reduced size, we can even sometimes to um, we need to diagnose the any kind of the disease, then we need to do the surgery. So but with the help of the optical fiber sensor technology, even we can insert the optical fiber inside the our mouth, through mouth in our human body, and we can diagnose the anything. And it's a low cost because this is made of the silica, and this kind of the sensor can work in the hazardous media, even the nuclear environment, under the sea, and all these places. So due to the low wavelength and optical signal, this technology is the immune to electromagnetic interference. And we can also develop the multi-parameter sensing, because um, just now I discussed that there are so many sensing parameters. So we can cascade the sensor, and we can develop the multi-parameter sensor. This is quite on demand nowadays. And a diversity of light propagation configuration, so we can mold the light flux as per our need, and we can just use for the say several various applications. Okay, so here our sensor is based on the plasmonics technique. So, what is the plasmonics? So, plasmonics is nothing but the coherent oscillation of the electron at metal dielectric interface. So, there should be metal and dielectric interface, and so let us assume this is the dielectric and this one is the metal. So, depends on the metal, like metal maybe the thin film or maybe with the nanoparticle based. So, if the metal will be like thin film based, then that is the propagating surface plasmon, that will create the propagating surface plasmon, that is the nothing but collective oscillation of conduction electron at metal dielectric interface under the influence of incident electromagnetic radiations. Means some electric field intensity will introduce after providing the radiations at the surface of the metal and dielectric. But in the case of the LSPR, we need to use the nanoparticle, and nanoparticles means the size of the particle will be less than 100 nanometer. Just a moment. Yeah, so here, this electric field intensity arrives around the nanoparticle, and that is very sensitive to the any external changes. Okay, so here our main focus will be on the this nanoparticle based phenomena. So here, just I want to discuss the two things like surface plasmon resonance and localized surface plasmon resonance. So here we can see everyone know about that optical fiber is made for the communication purpose. So we can also make the sensor. So how what we do that there is a core and cladding in the optical fiber. So most of the people just remove the cladding or fully cladding or partial cladding so that they can get the more and more evanescent wave at the sensing surface. And after removal of the cladding, they do the coating of the metal layer. So here we can see this is the combination of the metal and insulator. So due to that, when we will transmit the light, and then the one surface plasmon wave will generate. So here there are two kind of the wave, surface plasmon wave and evanescent wave. So when the propagation constant of both wave will match, then the resonance occur, and that phenomena is called the surface plasmon resonance. But in the case of the localized surface plasmon resonance, we do the coating of the nanoparticle at the surface of the after cladding, after removal of the cladding or unclad fiber. And here the electric field intensity introduced at the surrounding of the each nanoparticle, and that is the sensitive to the any changes. So actually what happened, let us assume that this is the nanoparticle, and after that nanoparticle is coated with the some of the biorecognition element to detect the particular things. Just I given the example of the glucose sensor. Okay, so due to the just combination of the biorecognition element with the analyte, some of the external changes occur, and due to that we get the wavelength shift or some kind of absorbance shift, or some people also claim the sensitivity based on the intensity change. So we can, based on the changes, we can get the sensor. Okay, so for that, our team had developed. Everyone heard about the tapered fiber, or so, but our team had developed the so many new kind of the sensor structure that we have given the name as the Waveflex biosensor. So, like here, we can see that this is the half tapered part. Means here, the firstly we tapered this. We have used the 125 micrometer. Just SMF28 single mode fiber, and firstly we have tapered for the 80 micrometer, and then a half part of that we have tapered again for the 40 micrometer. Okay, and this one we can see this one is 125 micrometer original diameter, and then we have tapered to the 40 micrometer, and then 80 and 60. So this is the wave like nature structure we have made with the help of the specific specialized instrument. And you can see these are the probe 1, 2, 3, 4, 5. There are 5 different probes, and those we have scanned the diameter, and that repeatability is quite high of this kind of the technology. So I will discuss about the fabrication, how we can do the this kind of the fabrication and all these things in the detail. Our team has also developed the double tapered structure, and as well as we have just developed the new kind of the structure, that is the humanoid tapered. So here this one look like the head, and this one is the shoulder, and this one is the hand. So we have given it the name as the humanoid tapered. And one more structure is that the tapered in tapered, because what we have done, firstly we have tapered to 80 micrometer, then again we have tapered to the 40 micrometer. So this is the tapered in tapered. And in the next phase we have done, we have tapered to the 80 micrometer, then again 4 times tapered to the 40 micro. So this is the new kind of the structure, that is the tapered in taper and 4 tapered waveflex sensor. Okay, we have also developed the double is tapered structure. So this kind of the fiber structure we have also developed. Apart from that, we have used the multi-core fiber, and that is the 7 core fiber for the sensing purpose. So here we have each day the core of the and diameter, external diameter of the multi-core fiber to enhance the coupling of the modes. So here we can see this is the just cross-sectional part is cut, and then we have each through the hydrofluoric acid, and in this part we have just east the cross-sectional external part of the diameter of the multicore fiber. And in this case we can see then in this case the core of the multicore fiber is expanded, but in this second case core is the same, only diameter is reduced. So we have used this property also in the Waveflex and biosensor to get the more sensitive and uh, sensor. Okay, so here you can see there are a lot of we have developed the new kind of the reflex biosensor. Like this one is the again new structure, we have tapered 60 and then 40 so many times. And this one is also the unique structure, and this one look like the crab structure we have developed. And this one is very just have a connection, because in actually normally in Indian language we say the namaste. So we have a design like that. So here we can see the original diameter was 125 micrometer, but what we did that we have taken the two single mode fiber, and then with the help of the fusion splicer machine we have uh, just a splice and make the bulge on the splice part. So we increase the diameter from 125 to 160 micrometer. Okay, and at the same time after that we have tapered to the 40 micrometer. So this is very unique structure, and this structure is also very unique, and this is look like a trident shape, or you can say in our Indian language like a trishul shape. So we have made this structure and to develop the sensor. And this one is also very unique structure. So question is that why we are doing like this, why we are making the this it look like the complex structure. No, this is not complex structure, we are just because due to this that we can increase the surface area, and we can increase the sensitivity of the sensor. Okay, so that's why we are enhancing the evanescent wave on the sensing area, and overall we are increasing the sensitivity of the sensor. So we can see that we have been developed so many probe, and we have measured the diameter, and those repeatability is quite high. So I will discuss how we fabricate these kind of thing. I will show the instrument schematic. So here, apart from the optical fiber, to develop the Waveflex biosensor, we have used the several unique nanoparticles. So especially the gold nanoparticle, silver nanoparticle, we have used, and PBA coated silver nanoparticle to just add on the localized surface plasmon resonance technique, LSPR technique. And apart from that, like graphene oxide, Maxine, and multi-walled carbon nanotube, molybdenum disulfide nanoparticle, copper oxide nanoflower. This is also unique nanoparticle we have synthesized in our lab. And um, so zinc oxide nanoparticle, cerium oxide nanoparticle. these nanoparticles we add on the apart from the gold and silver nanoparticle to just increase the biocompatibility, or we can say that these nanoparticle increase the surface area so that we can just that will load the enzyme or some antibody more on the sensing part, and that will help to enhance the sensing performance, like enhance the LOD and some sensing linearity range and all these things. So here with one schematic I will try to show that how this waveflex sensor work. So before that I want to just show one schematic that how we can do the fabrication of this kind of the sensor. So like firstly what we do, we just fabricate the new kind of the fiber structure which can uh, give the more and more evanescent wave, and that's will be very sensitive. And after that we do the synthesis of the noble nanoparticle, like here just given the example of the gold nanoparticle and graphene oxide that we have can easily synthesize with the turquoise method and modified hammer method. So after synthesis we do the characterization using the TAME and STEM SEM and some AFM and FTI, and we do several characterization before use, and after characterization you do the coating of the these nanoparticle on the optical fiber. So this is not easy, so I will discuss even the process in detail, that how we do the coating process and everything. So after this we coating of the nanoparticle, we again we do the just characterization of the um, mm, nanoparticle coated fiber structure using the SCM process, and through that we verify that all the nanoparticles are immobilized on the fiber structure or not. And then to confirm the material composition we also do the SCM EDX to verify it. And here after coating of the nanoparticle we do the coating of enzyme. So for that or we can say that biorecognition element, that may be the antibody or enzyme, anything. So for that I we need to follow some of the process I will discuss in detail. And after that the sense fabrication will complete, and then we can able to just do the detection. So this measurement process is very easy, not expensive. So just we use the tungsten halogen light source in the range of 200 to 1000 nanometer, and the spectrometer is in the same thing. And that we connect with the reaction stage, homemade reaction stage we have prepared in our lab, and the spectrometer can connect with the laptop. And here reaction stage means that is the way in our developed sensor we connect with the fusion splicer with light source and a spectrometer, and then we do the detection process. So here after measurement we also do the several analysis like reusability, repeatability, pH test, and um, pH test, stability test, and as well as the selectivity test. We do the several performance test before to say that this can be used for the clinical applications. So here, just I want to discuss the how waveflex sensor work. So let us assume this is I have shown the conventional tapered fiber. So in conventional tapered fiber, there are normally three regions. First one is the untapered part, that is the general region, then transition region, and then the most important is the tapered waist region, and we can also say that that is the sensing region. So here we can see when we transmit the light, then due to the tapered part, the fundamental mode transform into the higher order mode, and that will try to come out from the tapered waist region. And here tapered waist region, the more and more evanescent wave will try to come outside, and at this place we do the coating of the nanoparticle. Okay, so here when due to the this the localized surface plug phenomena occur, and and then some of the resonance occur, and that some electric field intensity introduced at the surrounding of the this nanoparticle, and that is very sensitive to any external changes. Say, if we can put anything on this part, then we can get the different some variation in the output signal. Okay, so based on that we claim the sensitivity. So overall, I have discussed that what is the Waveflex biosensor, how what are the new kind of the sensors we have developed in by our team, and then how we do the fabrication, how this sensor work. So based on that, I would like to discuss one or two sensor reflex sensor in today's talk. And I do not want to discuss this just in the brief. I want to discuss, I will discuss one sensor, but I will discuss in the detail about the each and everything about the fabrication and all this process. So here our team has developed one sensor for the bacteria detection, Shigella sonnei bacteria detection. In that, we have developed the uh, four-core fiber-based Waveflex biosensor, and we have used the sodium oxide nanorod, zinc oxide nanowire, and copper selenium gold nanoparticle for the enhancement of the sensing performance. And for the Shigella sonnei detection, we have used the Shigella sonnei antibody that is as a biorecognition element, and this work was last year published in the JLT. So question is that what is Shigella sonnei or Shigella bacteria? Shigella sonnei, Shigella is the four variant, and this is mainly Shigella sonnei and Shigella flexneri is the most important, and due to that um, especially in some drinking water or some food that come into our the body, and that causes the diarrhea, or some we can say the bacillary dysentery in human body. So we need to cure on time, but conventional technique was like PCR or plate counting method, in that we take the sample, and then on the plate we grow the bacteria, then we can see through the naked eye or something. That is the around 48 hours time or something time consuming process. So we have developed a sensor that can detect quickly this sensor. Okay, so here our team has developed the four W shaped four core fiber. So we have used the four core fiber, and we splice the multi-mode fiber on the both side of the four core fiber, and after that we have made into the shape of the W. Okay, so here we have also shown the field profile at the different stage of this sensor at the tapered part or at the multi-mode fiber at a different part. We can see that the mode profile is changing at the different location. So here in this case I will discuss how normally we do the fabrication of a Waveflex biosensor. So here this one is the first one is the fusion splicer machine of the Fujikura, and FSM 100. So it's two electrode and one camera is there, and there are two clamp, right clamp and left clamp, and that just we can keep the fiber, and then we can help of that we can do the splicing of the two different kind of the fiber. So here the multi-mode fiber core diameter is 62.5, and cladding diameter is 125, and similarly for the four core fiber, core diameter is 8 micrometer, but cladding diameter is 125. So this kind of the machine normally work as the cladding alignment technique, and that splice the two kind of the fiber. Okay, so with the help of that, we combine the MMFM with the 4 core fiber, and then again we do the same process at the opposite side. And after that, firstly, we use the combiner manufacturing system machine, and that is the seamless machine from the very high in instrument from the US. And here in this case, there are left platform and right platform, and there are three electrodes. So actually conventional tapered machine based on the hydrogen oxygen flame technique, and that do not give the good repeatability, and that very reliable. So this instrument we can see that based on the electrode electrode discharge, and through the that in three electrode is just arranged, and the 120-degree pattern that cover the surrounding of the fiber. And there are two cameras known to see the horizontal view and the vertical view of the during the during the tapering. And at that same time, with the help of the computer program, we just move the left platform and right platform. We stretch the fiber after the discharge, and with the help of that we do the tapering process. So the whole process do in the little bit, we create the partial vacuum so that there will be no any effect of the environmental surroundings or temperature or humidity, anything. So then firstly we with the help of the optimize the program, we tapered to the 80 micrometer, and then at two times we have tapered to the 40 micrometer on of the 81. So in this way we have made the W-shaped fiber structure. So now you hope you have gone through that the same process if you want to do any kind of the tapping. So we need to optimize. Yeah, of course, it takes long time to optimize the parameter for the specific kind of the shape, and to get the good repeatability once. And after just adding the just set the program, we can fabricate the thousand of the similar kind of the sensor, and with the high repeatability. So that is not a issue. So we have fabricated the fiber structure, and so after that we go for the nanoparticle immobilization and antibody functionalization. So for the nanoparticle immobilization, we let us assume that this is the W-shaped optical fiber structure, and we do the coating of nanoparticles. So before that, we do the three-step cleaning process. In that, first step is we dip the fiber in acetone, and just we take the acetone in the petri dish, and then we dip the fiber sensing part in on the acetone for 20 minutes. That removes the some of the dust or anything. And after that, we keep the piranha solution for 30 minutes. A piranha solution is the nothing but um, hydrogen peroxide and hydro sulfuric acid in the ratio of 3:7. And then we then we wash with the DI water. So this process creates the OH group over the fiber structure. And the cesium oxide nanorod and zinc oxide nano where we do the coating with the annealing process, in which we deep into the prepared nanoparticles, and then we heat it for the some times. And after that, for the gold nanoparticles, we need to follow the specific process that firstly we need to do the coating of the MPTMS. MPTMS is the kind of the reagent which can work as an adhesive for this kind of the to coat and do the to attach the gold nanoparticle. And because the MPTMS add the SH group over the is sensor structure, and after that we just deep in the MPTMS coated fiber into gold nanoparticles solution for 48 hours, and that golden particles attach over the fiber structure. And after that we wash with the ethanol and nitrogen gas so that unbounded nanoparticles will be removed. Okay, so this is the process we follow, the nanoparticle immobilization process. And similarly for the antibody functionalization, we do the dip the fiber in nanoparticle coated fiber into the NaOH solution that create the carboxylic group and for the 5 hours. And after that we dip into the EDC NHS so that activate the carboxylic group. And after that we dip the fiber structure into the antibody functionalization. So hope you have observed that we have not used any high-end instrument for the coating process. So we have just used the conventional method, and I'll show you the results. We got very good results with the help of this. So this is the advantage of this LSPR sensor over the surface plasmon resonance sensor, because in surface plasmon resonance sensor we need to maintain the just uniform thickness, and if there will be change in the micrometer or something, and then that we cannot get the good resonance wavelength in sphere, but in LSPR there is no such kind of the issue. Okay, so in this way we can do the coating of antibody easily on the fiber structure, and this way our sensor will be ready. Okay, so after that, to just detect any kind of the bacteria, firstly we do in the lab work. So in the lab we need to grow the bacteria, so we can buy the bacteria from the some of the company, or we can get it from the our in hospital. So from the culture lab, for that, firstly we need to grow in our lab. So for that we need to this is the typical process for any kind of the bacteria. Only the media of the bacteria, that is kind of the food of the bacteria, and just incubation time will change, otherwise the remaining process will be same for the any kind of the bacteria who any if any people want to do the work on the bacteria sensor, so they can follow this process. So we need to take the two 50 ml of 2 bottle water, and then we need to use the agar media, and without agar media we need to put, and then we need to autoclave for 20 minutes, and then agar solution we need to put into the some petri dish, and without agar media we need to keep at the room temperature, and then again we need to take the 50 ml of the media, and in that we need to put in the Shigella sonnei bacteria, and that we need to keep for 12 hours at 37 degree and 140 rpm and second incubator, and that will help to grow the bacteria. Then we need to dilute into the several lower concentration, and then we can go and do the detection. Okay, and this just for the reference, we can count the bacteria using the hemocytometer and our conventional microscope, and that we can correlate in the time of the detection. Okay, so here this is the experimental setup. I have already discussed that we have used the tungsten halogen light source and a spectrometer, and in this case we can just change the solution, and after that we can wash the fiber probe by PBS, and we can reuse it multiple times. Okay, so here in this case we have used the cerium oxide nanorod, and we can see the easily, and this is the zinc oxide nanowire, and this is the copper selenium and like gold nanoparticle, and this one is the FTIR result that confirms that the copper, selenium, and gold nanoparticles. So in this case, after team of the nanoparticle, we this one is the just a fabricated fiber structure, scanning diameter of the 6 probe, and repeatability is quite high. We have also measured the normalized intensity through the developed sensor, and we found that the peak wavelength was same. Okay, so after that we have this one is the original developed a fiber structure. So in this we can see that there are three tapered part, and after that these are the nanoparticles. All the nanoparticles are clearly visible. So question is that we have shown that this is the selenium oxide nanodot, this one is the copper selenium gold nanoparticle, this one is the zinc oxide nanowire. So how we can say that? So for that we did the coating of a uh, did the ACM EDX, and in ACM EDX we can get the all the desired material composition, and through that we can say that all the materials are immobilized on the surface. Okay, so we have also just did the ACM of a Shigella sonnei detected fiber structure, and we can see that bacteria found on the sensor surface. Okay, so we have from 10 to the power 0 to 10 to the power 5 CFU per ml. We have taken the concentration and detected on with the help of our sensor, and we found that there is a wavelength shift. So through that we have just drawn the linearity range, and its linearity is 1 bacteria to 10 to the power 5 CFU per ml bacteria. And we have also taken the buffer solution, and we have measured 15 times, and we have found that the standard deviation is quite low, and its stability of the sensor is quite good. And we have also prepared the higher and lower concentration of the bacteria in the different pH solution, and we found that the sensor is working better at the 7.4 pH, that is the equivalent to the serum. So we can say that this can be useful for the serum detection or in healthcare applications also. So it's a later on we have done the reproducibility test and reusability test, and that is also quite good. Then, then we have done the temperature test, the different temperature solution, and we found that at 37 degree the bacteria is alive and work, and we get the maximum wavelength shift. And we have also done the several kind of the analysis like a NaCl solution, STS concentration, and most important we have done the selectivity test. So in selectivity test we have taken the several other bacteria like S. flexneri, E. coli, Shigella sonnei, and so our sensors, and we are getting the maximum wavelength set in Shigella sonnei bacteria, not in the other bacteria, so that we can say that this sensor is specific for the Shigella sonnei, because we have used the Shigella sonnei antibody, so that react only with the Shigella sonnei, not with the other bacteria. So in this way we have done the several TMB test also, or some biofilm test for the just check the performance of the sensor. So in this way we have developed this sensor and verified this sensor for the with the help of the multiple test. Okay, so in this way we can develop the Waveflex biosensor. So I have discussed one Waveflex sensor in the detail. So in this way we have also developed a Waveflex sensor for the glyphosate herbicide in real agricultural product. And this one was published in IEEE sensor itself. So we have developed a sensor, a new kind of the sensor in that we have developed a new fiber structure and used the some gold nanoparticle, zinc oxide nanowire, and molybdenum disulfide nano sheet. And in the good thing is that in this we have also done the real sample test, like we have tested in the corn and soybean of this kind of the glyphosate herbicide, and this sensor work quite better in the sensing performance. So due to the time limitation I'm not going to discuss the more, but we have if anyone is interested in Waveflex sensor, we can go through our research papers and they can see. So we have designed several innovative sensor. This one, like this is for the ILT enzyme. We have published in biosensor and bioelectronics. So we have developed the innovative sensor in this surface. So I want to escape these things, and here in this we have used the multi-walled carbon nanotube and graphene oxide. So this one we have used for the histamine detection, and that is the humanoid shaped structure. That is also very unique structure that has been published in the Optics Express, and we can see the wavelength shift is clearly visible, and that differentiate the any all the uh, biomolecules. So here I told you that with the help of the this we can also differentiate the biomolecules. Okay, this one we have, this is very pretty well that, because we have developed the fiber ball on the one end of the fiber structure. And why this is quite good, because we have also collected the human serum from the hospital, and then we have tested with our sensor and the instrument available in the hospital, and with that our sensor is quite relatively been similar performance than with the instrument available in the hospital. So that's why we can say that our this sensor is useful for the clinical applications. So we have also developed cancer cell detection with the help of the uh, multi-core fiber. And earlier we have developed one more sensor for the bacteria detection, so with the help of the 7-core fiber. So that work was very much appreciable, and that is also we here we can see this is the Shigella sonnei we have grown in the this agar plate. And this is not single bacteria, this is the colony forming unit, CFU. So in the colony of the bacteria we can see with the naked eye. So yeah. if anyone is interested in the plasmonic sensor and optical fiber sensor, they can refer our recent book, that is the optical fiber based plasmonic sensor, the CRC press. And in the second book, geometric feature based, we have taken the different structure of the fiber, like U-shaped, tapered fiber shaped, interferometric based structure. So which one is the better for the sensing performance? We have written several chapter on this, so they can go through that. And recently, in last 2 or 3 months ago, we have published one more book on, based on the specific based on the biosensor. So if anyone want to go into depth of the nanomaterials and want to know about the development of the biosensor, they can read this book. So based on this last work, I have shown that bacteria detection, that is the we have received the IEEE JLT award from, and that was the quite innovative sensor, because that sensor can detect the bacteria within 5 minutes. So that is and its limit of detection is 2 CFU per ml. So that is quite good in compared to the earlier existing sensors. So as I mentioned that I also served the IEEE Sensor Council, and got the 2022 Best Performing Associated Leader Award from IEEE Sensor Journal. So yeah, so this is my team, and the nanotechnology team, and we have a also one more team in my lab in China. So thanks to all my students, my collaborators. So for this Waveflex biosensor, this unique Waveflex biosensor technology. So once again, I would like to thanks to the uh, organizing committee member of the Sensor Council to invite me to just meet you and explain my work. So hope I am able to finish on time. Now it's last 10 minutes is remaining to that will be open for the question and session. So if anyone have the question, please feel free to ask. And also I have written my email ID santosh@kaleuniversity.in. If you would like to do any collaboration, or if you want to know more about the Waveflex sensor, I will help to discuss. We can do the meeting. Yeah.